Okay, happy Thursday, guys. All ready to get started? Yeah. All right, I know this is like that weird part of the semester where you're kind of in that no man's zone between exams and stuff, but I do just want to reiterate like what we are covering in these next two classes, although like you're going to be looking a lot at this kind of stuff that are just I know are horrible to look at. This is one of the most important things in geotech, mainly because yes, it's important if you're in geotechnical engineering to know how to classify these. But as we were talking about at the beginning of the semester, every one of you guys, if you stick around in civil engineering, or even if you like stick around like in like site development or anything, you're going to be looking at geotechnical engineering reports, which are going to be using this language or whatever you want to call it. So knowing how to like decipher and read these things are important, and knowing what the different soil types are based off of their codes, and then also like which ones are going to be the problematic ones are going to be important. And I'll give you a leg up in the industry. So everyone's memorized this by now, hopefully, and have it posted on your wall and stuff above your bed at night. No. Obviously, this is a pretty like intensive looking chart, and I'm going to show another one later today when we talk about AASHTO. And like I don't expect you to memorize everything here. Actually, I don't expect you to memorize any of it really, because you'll always have the AASHTO or the ASTM reference to go to whenever you're working. But I tried to color coordinate it so at least you get a chance to like know some of the major aspects. So when you get a report on your desk, you'll be able to recall some of the major things to be like without having to reference everything. So for your exam too, I won't be giving you the entire thing, but I will give you snippets of this flow chart. And the main things that I want you guys to try to memorize, at least like when it comes to this USCS flow chart, is this first part, some of the key numbers here. So if the number 200 sieve is the first thing that we care about, if it's greater than 50% passing the number 200 sieve, then that's considered fine grain. If less than 15% is passing the number 200 sieve, then that's considered coarse grain. And this is an easy first part because that 50% is just the majority, right? Like, so if it's greater than 50%, then that means the majority of the material is going to be coarse grained. If it's less than 50% or vice versa or whatever, it's just whatever the majority of the material is. So that 200 sieve is the first one here. And that's going to be the thing that basically will distinguish between all the other ones. So if it's greater than 200 sieve, then we know we're going to either have a sand or a gravel. So it's going to be one of these two options. If it is less than the 200 sieve, or so like if it is greater than 50% passing the 200 sieve, then that'll be considered a fine grain. Remember, passing is just the stuff that is able to go through that 200 sieve. So if this is our 200, so this would be the passing percent, and this would be the retained percent. And it can get kind of confusing with all the percentages and passing, retained, or less than or greater than, because we're talking about less than or greater than a number, or less than or greater than an actual like sieve size. But that first step, just think of it logically, like larger material will be retained, smaller material will be passing it. And so if we're passing, then we're going to be the fine grain material there in the green on the left. So if we were to have a fine grain material, then the thing that we look for is the plasticity chart, which is the Casagrande plasticity chart, which we showed here. And so we basically can go straight to this, and this is where the Atterberg limits, which is a separate test, would need to be determined, where we will determine the liquid limit, and then we can calculate the plasticity index. So the plasticity index is calculated as the plastic index minus the liquid limit. Did I get that right? Or is it the other way around? Sorry. Delete that. Come on. So that is the liquid limit, which is determined using this experiment, subtracting out the plastic limit, plastic limit, which is this guy here, the hand. So we find that plastic index by taking the two measured values and calculating the plastic index. So once we find that, then we can find everything on our left. We just really need to know the chart there. So if we look to our right, though, if we have a coarse-grained soil, so greater than 50% is retained on the number 4 sieve, then the next thing that we look at is the number 4 sieve. Sorry, number 200 sieve. I might have misspoke earlier. So the next sieve we look at is the number 4 sieve, and that's to distinguish between sand or gravel. So saying we look at the greater majority, so is greater percent passing the number 4 sieve or is greater percent retained on the number 4 sieve? If greater percentage is passing the number 4 sieve, then we have a sand. And so the sand, we look at this next thing here where we look back at the number 200 sieve. So we kind of have to go back. We start with the 200 sieve, then we look at the number 4 sieve, and then we go back to the number 200 sieve. The number 200 sieve is a little tricky because if we have greater percent 12, then this becomes, we have to look at our plasticity chart again. So following this one here, we see a similar trend here with gravel. So anytime you have greater than 12% fines in either a sand or a gravel, we have to look back at the plasticity chart and we have to determine the liquid limit and the PI for that. If we have greater than 5%, or sorry, less than 5% fines, then we look at the grain size distribution parameters there, the coefficient of uniformity and the coefficient of curvature, which you're going to calculate in your lab if you haven't already done that. And if we have between 5 and 12%, then what we call this is like a group kind of thing. We call it SPSM or GPGM. And this is like a combination, kind of like a middle ground of classification. And the reason why I want to like highlight this right here, these are kind of like the default in geotechnical engineering. So a lot of times you'll get a report and it'll say SPSM on it. So if an engineer doesn't have time to actually go through and classify everything accordingly, doesn't have time to do a 200 sieve passing and the 4 sieve passing, and they have a sand, then normally what the default would be is this SPSM. So I'm just going to say most natural sands in Florida fall within that category, SPSM. So if you ever look at geotechnical engineering reports for like a low project, you know, again, like some like kind of, I don't want to call it like copy and paste project, but like your corporate projects like Wawa's or like Walmart or something where like the loading is known and it's standardized and you're just kind of doing your due diligence. A lot of times the geotechnical engineering reports will just, if there's sand encountered, then they'll call it an SPSM. And that's between 5 and 12%. So it's kind of that middle ground of it. If you have greater than 12% fines though, then that can either become an SM or an SC, or sometimes in that hatch zone. And these are kind of the tricky soils where they are primarily sandy, but also they behave like a clay in some instances. So a lot of times if you see the SC, SM, and SMSCs or whatever those are ones down here, this is like really popular in Ocala or like Gainesville, like the center of the state. We would have like those types of soils often. And those can be beneficial because they're really good to use it as fill material, but also they need to be classified a little bit further, and you need to do those Atterberg limits to really define how the plasticity is going to affect those. So in terms of like problematic soils, your organic, low plasticity and high plasticity silts, these are the things that might have issues. This one, obviously, if you usually encounter a peaty soil, most of the time, your client is just going to tell you to remove it, or the standard is going to tell you to remove it. There's very little that you can do to like densify organic soils. There's a lot of research going into like how we can mitigate that. How can we improve that type of soil without removing it? But most of the times you're either gonna have to redesign it or remove that soil. In Florida, 9 times out of 10, that peat soil will be at the surface, but there are areas in Central Florida where we call these things called like relic sinks or paleo sinks. Basically, they're really, really, really old sinkholes that have been like taking a bunch of trees in over time, and then covered with sandy soil. So sometimes you do get areas in Orlando and in Central Florida where you're drilling through and you're hitting nice, really clean sand, and then you hit a tree trunk, 50 feet down below grade, and it's just organic soils all the way down. And when you have something like that, that's really problematic. You usually have to redesign like the roadway. So if you're ever driving in Orlando or something and you're on a straight road, and then all of a sudden it does this weird little turn, most of the time it's going to be because there's one of those paleo sinks there that they just couldn't put the roadway over. So yeah, so that's what some of the major issues there. Well, again, like for the class, for the homework and for your exam, I want you to at least be able to like follow through these flow charts, this one and the AASHTO one. But I want you to try to remember some of those major like things, like the number 200 sieve, what is the thing that differentiates it, as well as the number 4 sieve, like what are the major categories there and the things you have to look out for. So we ended here on lecture 7. I'm going to do a few examples and then we'll get into the AASHTO. So I don't have the little slide before, but just as a reminder too, you will have a quiz that'll be published after class today. And then the labs, we do have Thursday lab today, and then the labs that are performed this week will be due next Friday. So just putting that on your radar. Next week I will be posting another homework as well, but no homework posted yet this week. Okay, so let's look through some of these examples. Example 1 here, this is again from lecture 7, so the one from on Tuesday. All right, so we have our sieve analysis right here. That's the one we just did. We have the Atterberg. This is the one that we're gonna do that's like really stupid. And this ASTM D2974. This is the one that I wish we could do, but we can't because it uses a lot of fire and stuff. So we have our sieve analysis. What we do know, we can calculate really quickly our percentage of gravel, percentage of sand, and percentage of fines. Because we know our number 200 sieve differentiates between coarse grained and fine grained, and then our number 4 sieve differentiates between our gravel and our sand. So what percentage of our soil will be gravel? 2. Yeah, and if you just fast forwarded, you probably saw that, but yeah, 2, because 100% minus 98%, that means 2% is hanging out above our number 4 sieve. So what percentage of our material is fines? Don't look at 38, 60, right? Because that's the 200 sieve right there at the very bottom. So anything passing our 200 sieve is going to be fine material. So that means 60% of our material is fines. Okay, so I didn't write that down. So, so for gravel, we have our 100 minus 98%. Am I like writing over it to give you guys these numbers? Oh, perfect. Okay. And then for our fines, that's our 200 sieve right here. So 60%, whatever. So right off the bat, do we know will this be a number that starts with either a C or an M or a S or a P or a G? Is it going to be a gravel? Is it going to be a sand? Or is it going to be either a clay or a silt? Clay or silt, right? Yeah, because right off the bat, that first thing, that 200 sieve, we know we're going to be going off to the left of our chart. Yeah, left of our chart. So we'll be hanging out over there on that other side. So the sand, our percentage sand, this will be 98 minus 60. So we have 38% sand. We can add that up. 60 plus 38 plus 2, that equals 100. So that makes sense. So the plasticity index, which is from our Atterberg limits, the index is always a calculated one. So we have our 22 minus 12, which means this is 10%. Oops. Now you'll see we also did a natural versus oven dried liquid limit. So what this would actually look like is we'd have to do this experiment twice. We take the soil, we do the liquid limit experiment, and that is 22 right off the bat. And then we do is we take that sample, we put it in the oven, we dry it out completely, and then we grind that soil back up because it's going to be like a little hockey puck. And so we grind that soil back up and then we redo the test after it's been oven dried and we look at the liquid limit after the oven dried state. So that distinguishes a little bit based off of the organic content, like whether it's going to be primarily organic or not. So we see that the liquid limit does change slightly. That ratio is going to be 0.82. And if you look at the chart here, 0.82, as long as it's greater than 0.75, then we're okay. We don't want it to change that much. Okay, so the main thing that we're going to be looking at for that first decision is the 60%. And then we also want to look at that plasticity index here too. So based off of here, we know that we're going to be hanging out over here on this side. So right off the bat, we can remove everything else. And then we want to look at our liquid limit. So is our liquid limit greater than or less than 50%? So it's less than 50%. So that means we are going to go down this path right here. And we need to look at our Casa Grande plasticity chart now to determine where we fall within one of these lines. So we have a liquid limit of 22. Come on. So we have a liquid limit of 22 and then a plastic index of 10. So that means we're going to be right here. So that means we will either be a CL or an OL. So we know we're either going to be one of these two options because we're above this A line in the hatch zone. So we already did the analysis there, but we had 0.82, and since that's greater than 0.75, that means our soil is a CL. So C meaning what? It's a clay. And then L meaning, what is L meaning? Come on in, dude. L meaning what? Clays are distinguished between their ability to retain their shape, which is what? Like, what do we call that? Plasticity, yeah, right. So like that's like exactly like in engineering mechanics and CE materials and all that fun stuff when we were talking about plastic deformation means it retains its shape whenever the loading force is removed. So that's like essentially what Play-Doh is. We can mold it, we have to have a force to mold it, but whenever we remove that force, it retains its shape. So same with clays and silts and stuff. So this is a clay with low plasticity, meaning it doesn't behave that much like Play-Doh, but it still does a little bit. So if it was a CH, high plasticity clay, that would mean that it retains its shape pretty significantly whenever we are forming it. So which one do you think, like from like a loading perspective or like an engineering mechanics perspective, which one would be a more better soil to have, a low plasticity or a high plasticity in terms of its strength? Low plasticity, why is that?
Won't be deforming every time it gets loaded.
Any other ideas? High plasticity, why? Why would high plasticity be good? So low plasticity, that makes sense, like because like when we think about deforming, we don't want plastic deformation, right? Like that's something that like our engineering brains are trained to not want to have. We want it to be below yielding. Why might like a high plasticity clay be beneficial or in terms of strength or capacity? So the way we characterize stuff is through frictional versus cohesive, right? Sand is going to get its strength from the particles actually like hitting against each other and locking into place. How do clays and silts, how do they get their strength? Remember like the little tiny, like really small little things sticking together?
Van der Waals.
Yeah, Van der Waals, all that weird like chemistry stuff that we were taught in like 5th grade, like Van der Waals and electrostatic forces, and what we encompass that in is cohesion and adhesion. So clays and silts get their strength, their engineering strength from cohesion. And that's like all of those weird electrostatic stuff making it stick together. And a result of that cohesion is the plasticity. So in this case, we actually have to retrain our brains for soil. A high plastic soil is generally going to be a little bit stronger than a low plastic soil, strictly because of the cohesion in it, because it's going to have a higher cohesion. Now, this is from the strength standpoint, but let's talk about like construction. So like if we had an excavator and we needed to actually start digging out this material, what would be an easier material to work with? A low plasticity or a high plasticity? Low plasticity, yeah. So it's one of those weird things where it's like, yes, like a geotechnical engineer is going to see a high plastic clay or like what we call a fat clay and be like, all right, I can work with this. Like we could, you know, it's going to have a significant amount of strength. But if that stuff is at the surface, then the contractor is going to be like, this is going to suck. Like we need to get rid of this stuff. You know, so it's like it kind of has that best of both worlds thing. So low plasticity clay or low plasticity silt is usually going to start to throw some red flags out in a geotechnical engineer's mind, where like a high plasticity clay is going to be like a little bit higher strength. But we'll talk about that strength later and stuff. I just wanted to get you guys thinking about it conceptually and stuff. Okay, so this is a CL. So let's talk about how we would further define this. So we know the group number, or sorry, the group symbol is going to be CL. So if you're showing your boring report and everything, then you'll see a little CL next to it. But sometimes we have to further define it, especially if you're with FDOT. You have to further define it based off of the name of it. So we have to have the group symbol, but also the group name. So in order for it to, it's official, you know, like legal name, it's CL. We would look at this chart here, the flow chart. And do we have greater than or less than 30% plus, or meaning retained on the number 200 seed? Remember this plus meaning larger than or retained. So do we have greater than or less than? Greater than. We have, yeah. We have 60% passing, which means 40%, or sorry, which means, yeah, 60% is passing, which means there's 40% retained on the number 200 seed. So we would have greater than or equal to 30% retained on that number 200 seed, which means we would only look at the bottom. And so then we would look at the, is there a greater percentage sand or greater percentage gravel? Yeah, we only got 2% gravel, 38% sand. So we have greater percentage of sand. And then we look at the gravel again, just to make sure it's like, all right, well, our double check here, is it, how much gravel are we talking about? Is it less than 15% or greater than 15%? As long as it's less than 15% gravel, which it is, since 2 is less than 15, then what we would have is sandy lean clay. That's what they would call that. So if you look back at like the list of options here, you can kind of like get a sense of like what we're talking about. If it's pure, just only lean clay, then that's like the pure form of it, right? Because we have less than 30% retained on the number 200 seed, and then less than 15% retained on the number 200 seed. So we have a CL value with very, very minimal sand. So it's majority going to be clay. So that's just going to be a lean clay. And then everything else has more and more like mixture material into it. So lean clay with sand, lean clay with gravel, and then sandy lean clay with gravel, gravelly lean clay, all that weird stuff. So again, this is like one of those things where like it's stupid and super frustrating if you're outside of the ability to like speak that language or whatever, you know? And so but if you can like understand this, then it'll make sense when the geotechnical engineer like refers to something as a sandy lean clay versus a gravelly lean clay, or a lean clay with sand versus a sandy lean clay. You know, it's stupid, but there are differences between that, and there is a method to these geotechs being super specific. Okay, example number 2. So for this one, we're just given a whole comprehensive sieve analysis. So this is very similar to our lab results here. So we have the mass retain, we have the sieve size. So what we're going to need to do is plot the sieve grain size distribution curve. So we'll figure out our opening sizes for our x-axis, and then the percentage retained. The percentage retained for each one. So that's how we would actually plot it. So we would have our gravel fraction here. So we know that this is going to be our gravel since it's above our number 4 sieve. So that's going to be what, about 2% gravel. 2%. So our fines, our percent retained here is going to be 5.94. So our percent fines really is going to be about 6%. And then the percentage of sand. So that'll be 94 minus 2. So we're just going to say about 92%. So the majority of our material is going to be within that sand range, right? So very minimal fines, very minimal gravel, 92% of our material is sand. So what should we expect the group number or the group symbol to start with? An S, yeah, right? It's going to be in that middle part of the chart there. So let's just follow the chart here just to show it. So we know first step is to look at that 200 sieve. We have greater than, or we have less than 50% passing. So the majority of our material is going to be coarse grained. So we're going to go over to this side, and then we look at our next step with the number 4 sieve. And this is basically asking us, is it going to be sand, majority sand, or majority gravel? And we have 92% sand and 2% gravel, so we know it's going to be majority sand. Gonna be on this guy here, so boom, we can just forget about that whole other side. And now we're only looking at, these are going to be our options here. So this is where we have to look at the number 200 sieve to determine whether it is going to be a sand, a silty or clay sand, or an SPSM, one of those mixture sides between 5 and 12. So the things, again, is that number 200 sieve, if we have less than 5%, then it's going to be a sand. If we have greater than 12%, then it's going to be a silty or a clayey sand. And if we have that middle part between 5 and 12, then we call this SPSM or SWSM. So which category would we go here? Percent passing. Yeah, so this is going to be one of those in between ones where our fines here is 6%-ish. So that will actually be this middle ground. So this is going to be an SPSM or an SWSM. So most of the time, if it's just a normal report, we assume everything is going to be poorly graded in Florida. And that's just based off of the geologic deposition. But in other places, we might have a nice, well-graded material. Like especially some of the like aeolian or some of the other types of sediment, like colluvial sediment, where it's like a little bit better mixed. It could actually be a well sorted or well-graded material. So if you have this middle part, if you're in Florida, most of the time, you're just going to assume an SPSM. But sometimes you might still need to look at your grain size distribution to determine whether it is a well-graded or a poorly graded. Because you can see that's the only difference there. The P is poorly graded, the W is well-graded. So we're going to look and calculate our CU and our CC from our grain size distribution curve. And you guys will get practice for this in the lab this week. So we find those corresponding effective diameters. So our D30, our D10, and our D60. And we'd read those over and find those accordingly, and then we can calculate those parameters of coefficients. Now, why do we care about these CUs and the CCs again? What's the benefit of that? or what do they do? What is the purpose that they serve?
Gives an empirical value to the qualitative chart.
Yeah, exactly. Yeah, I think you meant quantitative value.
Quantitative
Yeah,
value,
but it's
yeah.
like engineers, like we freaking love numbers for some reason. And so like instead of having this subjective interpretation of a chart where one person is like, oh yeah, that's a pretty curvy looking chart, or oh, that looks like a flat chart to me.
Yeah.
You know, it's like if anybody like skis or snowboards or something, like there's no standard for double diamond or like the rankings of the slopes and stuff, you know? So like a double diamond in one area might be like a diamond or a green in some other place, you know? So like an engineer saw that and was like, we're not doing that with grain size distribution because we're freaking putting numbers to this stuff. So that's what they did. They just created these values, the CU and the CC, so that now we have a standard way of categorizing the curviness of that chart. That's basically the whole reason for those. So then from that, they like were like, all right, well, who wants to like, what are gonna be the ranges? And some random engineer in the corner was like, let's just set it this way. And they're like, okay, that's fine. So that's what they did. They have these values here where if our CU is greater than 6, and our CC is in between 1 and 3, then we call that a well-graded material. If our CU is less than 6, and our CC is either less than 1 or greater than 3, so it's out of that range, then that will become a poorly graded material. So I know that looks kind of weird, like the way of saying it here, but the way I like to draw it, or just to interpret this, is let's say we have like a CU like line and then a CC line. Essentially, if we had 6 on the CU scale right here, if we had CU greater than 6, then this would be well graded. If it was less than 6, then this would be poor. And then our CC, our coefficient of curvature, has like a little range like this, where we have 1 and 3, where if it's in between, then this is well graded, and if it's outside, then it's poor. And the way these numbers work is you should always have both of these going on at the same time. So if your CU is greater than 6, then most of the time it should be very close to between 1 and 3. It's just the way the math works out with those two numbers. Now, it might not always be exactly like a perfect. That's why we have these two thresholds. And it might not always be because it depends on the sieves that you use that actually produce that curve. But we have these two thresholds where usually it's like, okay, if one of them is close, but one of them is true, then we'll consider the well graded. And if it's the other way around, then it's the poorly graded. Is that making sense there a little bit? Hopefully you'll see that in the lab again this week, where we have the different seed. The seed choice depends on or will result in the different values that we get. So regardless, right here, for our grain size distribution, we have a CU that is 3.6 and a CC that is 0.82. So based off of this, would that be poorly graded or well graded? So 3.2 is like right here, and then 0.82 is like right here. Yeah, so we're poor graded for both of them. So we can be pretty confident that this would be a poorly graded material. So that means we're going to have an SPSM, which most of the time is going to be like that because most natural soils in Florida are poorly graded, not well graded in Florida. So that would make sense. So SPSM is going to be that middle one there. Okay, so once we have the SPSM, what do we call this now for legal work, for legal purposes? We look at the first starting point in our ASTM chart there. So SPSM, so luckily we're just focusing in this one right here. And if we have less than 15% gravel, which we do, because we have 2%, then we would have a poorly graded sand with silt, which is what we would call this then. Poorly graded sand with silt. So that's its legal Catholic name or whatever you want to call it. So if anything, by the end of this class, hopefully you remember the carrots. This is less than. You're gonna be reading a lot of those and greater than, right? It's always wanting to eat the larger thing. So it's always trying to eat the larger one. Whatever. So a lot of reading that stuff. Okay, so just for fun, you can see now like one FDOT report, like let's say again, you're working for like a contractor or you're working for a roadway, like transportation. I know a lot of you guys have said like transportation is something that's interesting to you. You're going to be needing to produce transportation profiles in this huge like 400-page report that you're going to send to FHWA or the city or FDOT. And so in order to create those roadway profiles, you're going to need to look at the geotech reports, which would look something like this. And you can see now what these classifications mean as they start looking down. So FDOT requires the group number, or sorry, the group symbol, but also a description term, so light brown, and then the actual professional legal name. So fine sand with silt in this case, or light brown clay fine sand here. You can see most of the time, if we just have a sand that has no lab testing associated with it, then we're going to call it an SPSM. And that's based off of the geotechnical engineer's like experience in that area. So they may have done a bunch of tests in a similar geologic deposition like last year. And so they don't have to charge the client for a bunch of lab testing like fees because they know that they've already tested in that geologic like formation and they already know like the type of soil that's there. But every once in a while, they'll still have some lab testing that shows some of the like the justifications for the classification. So you can see right there at a depth of whatever that is, the minus 200, that means the percent passing the 200 C was 12%. So that would make that a silty fine sand, SM. And you can see down here, dark gray, down here, this is still SM because we have 41%. But that's because this is between 12 and 50%. So SM is that range in between that. Yeah. So now the whole goal of this is these single borings, and we'll talk about it in site investigation, but we take these single point measurements, we do the classification, we know that this soil at this layer is one thing and the soil at another layer is another thing. So we have to look and try to group like soils based off of this classification, and from those like soils at different depths, we can produce the soil profile, which is then the thing that you would give the roadway or your client or whatever you want. And this is the thing where they're just like, oh, this makes sense to me now. This is what I should expect underneath our soil, underneath our site. So we should expect a sand, silty sand, and then this large layer of silt or whatever in this case, where there's just two borings. Of course, you're doing this with like multiple borings, not just two. But you want to try to paint the picture for the client on what to expect underground and the different like changes of it. So yeah, some good examples of this. So this is actually from here, somewhere in Jackson. I think it's up north in Rybald or something. You can see how quickly things actually change. Here, where if you have the lab testing shown there, then you can assume the samples next to it are going to have a similar property. Okay, so the key points for the USCS, yeah.
In the July report, there's like the first couple of layers is HA.
Yes, yeah. HA is a hand auger. So that was the very first lab that we did. Remember these numbers here represent the SPT blow count that we'll talk about. So that's correlated to the soil strength, and that's a way that they like can estimate the soil strength. So the higher the number, the more resistance the soil has, and the stronger the soil is. But remember, for a hand auger, we always do the hand auger to a set depth to check for utilities, to make sure we're not pushing through something. And in this case here too, you can see they actually had to drill through asphalt. So they have 6 inches of asphalt and then the lime rock base and all like the transportation, the structures underneath it. So they hand auger through that, so they're not destroying the whole road. So yeah, that's what that HA stands for. Okay, so for the USCS, Unified Soil Classification System, it's a primary classification system for soil in the US for any structure report. So if you're ever doing a bridge, if you're ever doing a building, if you're ever doing a retaining wall, if you're ever doing any type of like structure thing that's going to apply loading, so like even MSC walls and stuff, you would have to classify the soil under the USCS classification. It involves the two group symbols, so the two group symbols, and then this descriptor group name or like formal legal name that you have to worry about. It's based off of the two types of soil. The first thing that we look at is organic or inorganic, and then the three primary soil grain sizes, so gravel, sand, or fines. And then we use plasticity to define the fines. We don't look and define the clays or the silts based off of the size of the particle. We use it to define it, or we use the plasticity to define it. So the plasticity, high level of plasticity is 50%, a low level of plasticity is less than 50%. And again, that's just like Play-Doh. So high plasticity behaves a lot like Play-Doh. It'll stick together, it'll hold permanent deformation. Low plasticity still does a little bit, but not to the same extent. So they just chose that 50 value there. That 50% is kind of like a Achilles heel there, that very arbitrary value that was chosen in 1948. So there are some research now, and there is starting to become a push for a better, more like empirically based classification system. Instead of just assuming 50% is going to be the deciding line, now we're looking at developing other types of ways based off of fine plasticity, so different stages of liquid limit instead of just that set 50%. And these are made more so based off of the engineering design parameters. So if you remember when we were talking about asphalt, we were saying like, oh, the design for super pave and asphalt is all based off of its performance. So we don't like test like the tensile strength of the asphalt, we test the fatigue strength, like how it actually performs. So now there's a push of doing that in soil analysis as well. So we look at more so how does the soil react under its mechanics, its fluid flow, and its shear strength, and how can we classify it based off of that, rather than a test where we just roll the soil in a Tootsie Roll and see and find the moisture content, which is what we're going to be doing in a few weeks. So yeah, hopefully by the time you guys are old like engineers, we will be working with a more like data-driven, like more empirically based analysis, not something from World War II. But for now, we're still working with the World War II stuff. All right, so for the one of you who actually likes this kind of stuff and likes flowcharts, this is kind of a fun challenge. It's not homework, I'm not gonna actually assign it. But if you can see, this is all just like a flow chart, right? So if any of you actually do like coding or like Excel spreadsheets, and that's like your love language, like mine, then like you can kind of actually produce an Excel spreadsheet where if you put all of these things in through a series of if statements and coding and all that stuff, then you can actually produce something that can output it automatically. So kind of just a fun challenge, not necessarily, but you know, that's one of the benefits of this type of system is that you could produce this, which means there's software that out there that will produce it automatically. All right, so let's go to AASHTO now. A lot of the things in AASHTO are similar, it's just a different flow chart, so we'll go through that kind of quick. Okay, AASHTO. Uh-oh. Okay, AASHTO. So, world's longest acronym. What does AASHTO stand for? I never remember either, so it's okay. I'm just gonna go through these because we just started talking about that. This is more, or that's the same one we went through for USCS. So just ignore all this stuff. We already did these examples for USCS. There is another example here if you guys do want to go through the USCS one in your notes. Okay. So AASHTO one. So this is ASTM, it's also an AASHTO standard. AASHTO is the American Association of State Highway Transportation Officials. This is what happens when all the engineers get together at conferences and stuff. I just decided to freak everybody out. So we talked about USCS again, structures. If you think of like high rises and bridges and stuff that's going to apply loading, then think of USCS. If you think about stuff that people are going to drive on, so for roadway projects, then we have to think about AASHTO. That's the classification there. So I know all of these slides are going to look crazy with all these things. So I try to like color coordinate in the background if you do print them in color so you can reference them quickly, because these flow charts, especially for the PE, primarily whenever you had to actually take like paper exams or paper like references, you know, like you'd be flipping through stuff and accidentally flip to the USCS classification when you need the AASHTO one. So that was an effort for this, but just ignore the colors if you don't print them in color. All right, so the AASHTO was developed, like surprise, surprise, a really long time ago still. So 1929 to 1945, when public roads boomed. This is even before like the interstate system. You know, the interstate system was like in the 60s, like 50s. So this is even before that, but when they started like developing these public roads that like stretched from different jurisdictions, they're like, maybe we should figure out a way to like ensure that all these roads work so everybody can travel. So the soil is rating for roadway subgrade. So the audience that we're producing these for is going to be for subrage is for transportation engineers. So we're basically needing to tell them how suitable the soil is to be used in roadway subgrade. Remember, the subgrade is the first layer. That's the thing that's compacted before they put the layer of aggregate and then either the asphalt or the concrete over it. So the subgrade could be either really, really nice if it's natural soil, or it could get really, really expensive if we need to bring fill soil in from like a different area in the state or the country. So what the transportation engineers want to know is the current soil on site, how well can we keep that soil there? Or do we have to actually bring soil in from off site? So it's somewhat simpler, but it is a little less intuitive, but it's classified into 8 different groups. So the USCS has a bunch of like whatever combinations of things, but for AASHTO, we only have 8 primary groups, but then we have several subgroups, which we'll talk about in a little bit. And the main big picture things that we want to look for is these values here. It's always going to be A for AASHTO and then a number after it. So A8 through A8, or sorry, A1 through A8. So those are the 2 ratings. So A1 would be the best soil for subgrade. Like, so if you're a landowner and you have A1 soil on your site, then you are like, you're rolling in it because you can sell your soil to the to the government for some good money there. But if you have A8 or A8 soil is encountered, then basically that's like, okay, we don't want that stuff. So A1 through A3. This is going to be well, the 3 ranges are there. A1 through A3, this is our granule material. And this is usually considered excellent to good. So A1 is going to be the best type of fill material for subgrade that you can get. But as you probably imagine, it's very rare to have like true A1 soil. So usually if it's A1 to A3, then we're like, all right, this is good stuff. We can work with this. A4 to A7. This is going to be mainly your silty and clay material. So this would be similar to like our SMs and our SCs and stuff. So it's going to still have some sands and some clays, but it's going to have some level of plasticity to it. So this is going to be considered our fair to poor. And then A8. This is going to be our muck, organic, and peat and stuff. So this is, if you have A8 soil, or, you know, organic, then most of the time they're going to have you remove it from the site and you're going to have to bring fill material in. So you can't necessarily use it. So A8 is going to be the worst case. So it's kind of a little bit more intuitive. A1, good stuff, all the way down to A8, which is bad stuff. So, but not only do they look at those first groups, we also have these subgroups. So the way that the classification system works is you have A, again for AASHTO, because the AASHTO engineers want you to remember who you're talking about. So A for AASHTO, and then that second number is going to be either 1 through 8, but then you have a third number and potentially a fourth number. So the first one, the one shown in gold there, those are the group numbers. So that's from the flow chart that we're going to talk about on the next slide. Sometimes you would have a second classification, or sorry, it's there. Okay, yeah. So then you would also have the subgroup, which is that gray number. That's not always used, but sometimes it needs to be used. This is going to be similar to like the SPSM or the SMSC, like that, like kind of combination area. And then you would have a group index as well. So the group index is a classification system that's based off of an empirical equation, which means it's based off of data set that was actually used to test whether the material works as a roadway subgrade or not. So the key differences to look for compared to the unified soil classification system, fine versus granule material, they use a 35% dividing line. In USCS, what was it? What was the percentage for the fine / granule? 50%. Yeah, it was just majority rules, right? Is the majority granule or is the group majority fine? But for this, they have 35%, so it's a little less intuitive for it. There's no coefficient of uniformity and there's no coefficient of curvature. So in order to define that shape of the grain size distribution curve, they actually use the group index, which is this gnarly looking equation that I'll show in a little bit. Now, luckily, most of the time you're going to have some software that will calculate the group index for you automatically, but still you need to know the basics behind the group index for that equation. They do have a plasticity chart to divide it, but their plasticity chart is a little different than the one that USCS looks like. It's similar looking style of reading, but the lines are different. And so their category divides high plasticity versus low plasticity at 40% liquid limit. Just to confuse us because they wanted to be different. Actually, I don't know which one came first, but like, yeah. So remember, USCS used the Atterberg plasticity chart. That was 50% dividing line. So now they're going to use one at 40% dividing line. So that's going to be the key difference there. So if you look at the flow chart, I think it's a little bit nicer, like tropical starburst colors, you know, a little bit, but it's a little bit easier to read. There's less like kind of overlaps and stuff. Because there's really only 8 major categories, and then you'll see those subcategories there too. So the first one, of course, A8, that's going to be the same one off to the left, where that is our organic material that's really crappy, and we just get rid of it. Our silty clay material, so that's going to be that 35% or less, number 200 seed. So if we have less than 35% passing the number 200 seed, then that's our granule material. If we have greater than 35% passing, then that is going to be our number, or that's going to be our silt and our clay material. So on this side, the good stuff is all off to the right, and then it gets worse and worse as we progress off to the left. So just to show you the plasticity chart for AASHTO, again, looks kind of similar, right? Yeah. So.
Back on the last one, why is there a reason why 1 and 3 are grouped together and then 2 is?
Yeah, that is a good point. Yeah. So
I guess, yeah.
Yeah, these are all very similar in like quality. Like I said, I had the A through 3 are like kind of the same, but they're all very similar in quality. So these are more like realistic, like what we'll find. Like our A3 is very like a very specific type of soil. But yeah, that is a good point. They are distinguished between that. You would never have like an A3 dash something. So when it comes to like its quality, it's kind of like close together. So A3 would still not be like as good as a fill material for compaction than A24 or A25 or any of those center ones. Because if you think about it, we actually want some amount of material to still compact it and achieve this density. So yeah, that's a good point though. It's kind of like not the best flow of it over there. But. All right, so the AASHTO plasticity chart, very similar way of reading it. We have the plastic index here. And then we have the liquid limit. These are all just in percentage. And so we have that 40% is the dividing line here. And we would just read this based off of the range at which, or whatever zone we have values in. So if we had 70 and 20, then this would mean our soil is either an A27 or an A75. So you would have to make that distinction on it there. So this is the plasticity chart for Atterberg. So again, it seems like there should have been some copyright stuff. It's very similar there. And they like to confuse you. And this is an area where the FE is gonna love to see, like, check you, because it's, again, fast-paced test. They're gonna give you the liquid limit, or they're gonna give you the AASHTO, and they're gonna give you both of these charts. And so you're gonna have to read through the problem and make sure they're looking for the correct classification so you know which one to read and based off of it. All right, so the group index. Group index is that very last part of the classification. This is similar to like the group name that we have in USCS. So the group index is just like a number that classifies its ability or the quality of the soil. So it's an inverse relationship, so it's a little non-intuitive there, but as the group index goes down, so the lower the value, the higher the quality. So if we have a really high group index, then that soil is not going to be very well suited for subgrade material. So the nice thing is, if we have a soil that is an A1, an A2, or an A3, so in that excellent to good category, then we don't even have to worry about calculating a group index. We're just gonna, the group index is 0 there. So that's the best quality that we have. Really, the group index is only used to classify some of the more plastic materials or some of the more fine materials. So if you have an A2 and an A6 or an A2, A7, or sorry, A2 or A27 or A26, then you would use this equation for the group index. So PI meaning the plasticity index. Which is the liquid limit minus the plastic limit. And then this F200, this is the percent passing the 200 seeds. So sometimes this is shown as F.C or fine content. So that's just what that means, F subscript 200. This is taken from the AASHTO manual, so that's why I use the same notation there. So again, this is one of those if statements. So if our soil is A1, A24, A25, or A3, then our GI is 0. But if our soil is A26 and A27, then we use and have to calculate the GI value. And then if it's anything else, so if it's not one of those, then we have to use this further empirical equation here. So what do those numbers actually mean? And so like if GI is a negative value, if you calculate that as a negative value, then we just always show it as 0. So you'll never actually see a negative value. We'll just assume it's such a high quality that we're just going to put it as 0. GI is always rounded to the nearest whole number as well. So it's one of those things where it's an empirical relationship. You know, we're not super precise, so you're just going to round up to the nearest whole number. There is also no upper limit for the GI value. So like, you know, there's a lot of like fun things looking in like what is the worst type of soil that you could ever have, and all these like different areas fighting for the worst type of soil, so the highest GI number. But generally, if a GI value is greater than 20, then this will make a very poor subgrade. So GI should also only be used for comparison between soil in the same group number. Because remember, we have different GI equations for the different group numbers. So really you would just compare if you had if you were comparing an A26, you had 2 different sources of A26. So farmer A in Ocala is saying, hey man, I got some good soil on my land, like come and take it. And like it's an A26, and then farmer B up in like Micanopy has some same A26 stuff. You're going to calculate the GI for both to determine which one you're actually going to use. But if you have like a different type, like an in whatever, A4 soil or something, then you would only compare it in the same ones. Okay. All right, so let's look at an example of these here. So for this soil, we have our sieve analysis. So we know that our soil is 6% passing the 200 sieve, so that means it is going to be a granule material since it is less than 35%. So if we look at our chart, boom, we can get rid of everything on the left. And we're going to deal with a 35% or less. So do we have less than 25% passing the number 200 sieve? Yes, because we have 6%. So what we look at now is our sieve is non-plastic, we're assuming, so there's 0 there. So we know that this is going to be group number A1 because we have less than 50% passing our number 40 sieve. So we know it'll be an A1A because of all these things. Our plasticity index is less than 6. And we have less than 15% and less than 30%, less than 50%. So it'll be an A1A. So for GI, be 0, right? So technically the AASHTO classification, if you wanted to be very precise, it would just be 1-A, and then in parentheses for the group index 0. Because if we have any of these soils, we don't worry about a GI value, so we don't have to calculate it. So that's super nice. So that's mainly not going to be the case. You rarely ever see like A1 soils. There's some like sites that were A3 or like A1. But most of those are going to be mines now because the person realizes that they can just use that soil and sell it. So most of the time you are going to have some type of silt and stuff. And so you are going to find like an A2 or an A4 type of soil. Okay, so in this example, we have a little bit more sieve data, and we also have plasticity data down here. So we know we're going to have a material with some plastic behavior. So we're still right on that threshold. We're still less than 35% of our passing 200 sieve. So that means we're still going to be classified as a granule material, which is nice. So if we look over here, then we're going to look at our granule side. We have less than 35% passing the number 200 sieve, or less than 25% passing the number 200 sieve. So in this case, we have 34%. So we have less than 35% passing the 200 sieve. Okay, well, it didn't show it there. Well, so anyways, right here, we have the two decisions. If we have less than 25%, then we go this right. But if we have less than 35%, then we go this route. So it's not it's a weird looking decision tree because it's not like there's two different, it's like two different categories essentially. It's not like one's going to have less than 35, one's going to be greater than 35 like USCS, but it's more so like which one do we have, if like the special case where it's less than 25 or greater than 25 but less than 35. So that's another way of like writing that down. So in this case, since we have 34, we're going to be here because 34 is not less than 25, it's greater than 25. So then here we look at the liquid limit and plastic limit on the number 40 sieve. So that's just the like the Atterberg test that we were talking about. So our plastic index is 12. So that means our plastic index is here, 12. So it's going to be considered clay. So then we look at the 40%. Are we less than or greater than 40% for liquid limit? We are less than 40%, which is right here. And so this is our 826. So I should say all of this right here, you can use the flow chart, or you can also use the plasticity chart. They'll essentially tell you the same thing. If you look at the plasticity chart, you can see that like that's the same categories. I'm just putting it in decision tree form or whatever. So for the group index, 826. Let's calculate our group index. So for an 826, we would have to use that middle equation, so 0.01 times FC, or percent passing 200 seed minus 15, and then a PI minus 10, multiply those two. So it should, this is always going to be shown in percentage form or calculated in percentage form. So if we show that math, 0.01 times 34, which is our percent passing, our 200 seed, minus 15, and then 12, which is our plasticity index. Because remember, plasticity index is plastic limit minus, plastic limit minus the liquid limit. I think this is messed up. This should be backwards because PI should be liquid limit minus plastic limit. This will be illustrated more in class because liquid limit is the moisture content at which the material starts to behave more like a liquid. So that should be higher than the plastic limit. So I'll double check that and reiterate that. It always gets mixed up. So those values should be reversed, I believe. I think the liquid limit should be the higher one, because that doesn't make any sense.
That would be the negative number.
That's what I'm saying. The equation for the plastic index should be the liquid limit minus the plastic limit. So the liquid limit, I think, should be 49, and the plastic limit should be 37. Those numbers should be switched. So I'll double check that. Regardless, though, we calculate the PI of 10 because the PI should never be negative. If the PI is negative, then the input is wrong. All right, so GI, so we're gonna say that's equal to 0 because we round to the nearest whole number. So still our AASHTO classification is 826 and then with a 0 after it. So that's kind of nice. All right, one more we'll go through really quickly. So again, looking at that 200C, we first looked at the 35. So this time we are greater than 35. So that means we're going to be here on the left. We know it's going to be a silty clay material. So before that, then we look at the plasticity chart right off the bat. Again, this should be switched. You just switch those values. So we can look at the plasticity chart. Our liquid limit in this case is 43. Even though it's probably wrong. And then our it should be 12. So our plastic index is 12. So in this case, if we did this out, 43 minus 30, which is what this line represents. And we can see that it is actually greater than. So that's a tricky thing. Sometimes you have to, you can't really read this chart most of the time. Like let's say this is 43 and this is 12. Now, what side of it are we on? So you have to actually use the equation of that line to determine. In this case, since we are at 12 and we are less than 13, then we should be in A75, which is down here. We would use that there. A75. So we aren't done. We have to find the group number. So for that, since we're in A75 territory, we would use that last equation. Plugging everything in there. We can see our group number is 6.745, but we would never show it as 6.745. We would just say 7. So our AASHTO classification that we would send to DOT is A75 and then 7. So the key points to AASHTO, again, this is only for roadway reports. So FDOT is like they're going to care about AASHTO classification. But if you're building a bridge for FDOT, if you're building an MSC wall or retaining wall, you still use the USCS classification. So this is only for roadways. So FHWA and just general driving roadways, any place where you care about the subgrade. So general trends again there. The key difference is that 35% passing the AASHTO. Where for the USCS, they are saying 50% is distinguishing between granule and other material, so silt and clay. So for them, for AASHTO, if it's a silty or clay material, then we use that plasticity chart. And remember, those plasticity charts are different between the two there. The other key difference is for USCS, they say a liquid limit of about 50 is to separate between high or low plasticity. And then for AASHTO, they have a relationship of PI with as a function of LL. So essentially, this line is the thing that distinguishes between high or low plasticity between those two. A clay or silt. So they use that. It's a different function. All right, so this is a table just to help like kind of reiterate some of the similarities between them. In Florida, most of your soils that you come across are going to be like an A24 or an A26 natural soils. So that's our SM and our SC. Yeah, so those are the very similar ones. So most like natural stuff is going to be somewhere around that range. So if you're ever in doubt, like, you know, just say A24 or an A26-ish. But it's not a one-to-one comparison because they're completely like different like standards. So you can't like really compare them. But it does help if you know you have a site that has a bunch of like sandy material, then you should expect somewhere between like an A1 to an A3-ish. All right. So I know that's a lot. Try to focus on those key points. Remember, I'm not going to make you memorize the whole like output of it for the exam, but those key points you will need to know and be able to recall. And I will give you like the plasticity charts to at least know how to read. So make sure you know how to read those plasticity charts. So the quiz will be published here in a little bit. We do have lab here at the end of class. And nothing else until Tuesday. So we'll start subsurface investigations.